Okay, so we're going to do discussion 9.1, Intro to Redox Reactions. I just want to say that if you are my student, it's really important that you focus on this unit because we're going to feature it heavily in our option. Alright, so what does redox mean? Redox stands for oxidation and reduction reactions. And these are reactions that are characterized by a change in the oxidation state of one or more elements. Now we see this change in oxidation state because electrons will be transferred from one species to another during the change. And we can see which substance gains or loses electrons by looking at the change in oxidation state of an element from one side to the other. So it's really important that we're able to assign oxidation states to each element. Now some atoms will always or almost always have the same oxidation state. So any element that's on its own, including the diatomics, will have an oxidation state of 0. And this is because elements are made up of atoms, and by definition atoms are neutral. Ions, whether they're free ions or ions bound in an ionic bond, they will take their expected ionic charge. So alkali and alkaline earth metals will be +1 and +2 respectively. Oxygen is almost always -2, except if it's in a peroxide compound, in which case it's -1. Hydrogen is almost always +1, except when it's in a metal hydride, in which case it is -1. For compounds, the sum of all the oxidation states of all the atoms in the compound will sum to 0, because by definition compounds are neutral. For polyatomic ions, the sum of the oxidation states will equal the charge on that polyatomic ion. And it's important to note, if both elements in a compound don't have a rule associated with them, then the more electronegative atom will take its expected ionic charge. And we'll see an example of that on the next slide. So let's go ahead and practice this. So for nitrogen dioxide, it's a compound, so I know that the oxidation states will sum up to 0. Now we have a rule for oxygen, but we don't have a rule for nitrogen. So we're going to use the charge of oxygen to figure out the charge on nitrogen. So oxygen we know is -2. And since there are two atoms of oxygen in nitrogen dioxide, the total negative charge will be -4. That means in order to balance out the negative charge, the positive charge has to be +4. Since there's only one atom of nitrogen in the compound, we know that that atom of nitrogen must have a charge of +4. The next example is the carbonate ion. Because this is a polyatomic ion, the sum of the oxidation states will equal its charge. So again, we have a rule for oxygen that says it's -2. Since there are 3 oxygen atoms in the ion, the total negative charge is -6. That means that the total positive charge has to be +4. Since there's only one carbon, it will have a charge of +4. For chloric acid, we have 2 atoms that have rules associated with them. So we know that oxygen is -2 and hydrogen is +1. So we'll have 6 units of negative charge from oxygen and 1 unit of positive charge from hydrogen. So the total amount of positive charge required to make the compound neutral will be +5. Since there's only one chlorine, it will have an oxidation state of +5. Now I want you to take a moment and pause the video and try these next 3 on your own. Please note that the cyanide ion down at the bottom has 2 atoms for which we do not have rules associated with. Okay, so in nitric acid, that's a compound, so the oxidation states will sum to 0. We have oxygen, which has a rule of -2, and hydrogen, which our rule says is +1. So we'll have 6 units of negative charge from oxygen and 1 unit of positive charge from hydrogen, so the positive charge on nitrogen must be +5. In the next example, we have an ionic compound, calcium nitrate. Now, in an ionic compound, any of the ions will take their expected ionic charge. That means that we have a rule for oxygen and a rule for calcium. So oxygen will be -2, as always, and calcium is going to be +2 because it's a polyatomic ion. So here we have 6 atoms of oxygen, so we have 12 units of negative charge coming from oxygen. We know that calcium is +2, so there's our +2 from calcium. That means the total amount of positive charge coming from nitrogen must be +10. But since there are 2 nitrogen atoms, each one will have an oxidation state of +5. Okay, so in the cyanide ion, we have to look at the electronegativity values of carbon and nitrogen. Nitrogen is the more electronegative element, so it will take its expected ionic charge of -3. That means that carbon has to have a charge of +2 in order to make the ion have a charge of -1. So carbon will have an oxidation state of +2. So some definitions. Oxidation refers to a loss of electrons or a gain of oxygen or a loss of hydrogen. And we saw that in Unit 3 when we talked about the oxidation of alcohols. Reduction is the exact opposite of oxidation, so it is a gain of electrons or a gain of hydrogen or a loss of oxygen. And we'll see that in Unit 10 when we talk about the reduction of different organic compounds. So the reducing agent is the compound or ion that contains the atom that was oxidized. Now we call the thing that was oxidized the reducing agent because it is freeing up electrons for the other species to gain. And the oxidizing agent then is the compound or ion that contains the atom which was reduced. Now we call it the oxidizing agent because it helps the other species become oxidized by accepting its lost electrons. Alright, so if we use the oxidation numbers and look at the change in oxidation state from one side of the equation to the other, we can see which species is oxidized or reduced. So an increase in the oxidation number indicates that an atom has lost electrons and was therefore oxidized. So if you see the oxidation state becoming more positive, that means that species was oxidized. A decrease in the oxidation number indicates that an atom has gained electrons and was therefore reduced. So if you see the oxidation state become more negative, you can say that that species was reduced. So in this example, we have zinc reacting with copper 2 sulfate to form zinc sulfate and elemental copper. So I've assigned oxidation states to each of the atoms, and you see that the elemental zinc and copper have oxidation states of 0. In the ionic compounds, they take their expected ionic charge. So if we look at the change in oxidation state for zinc, we see that it goes from 0 to +2. That is an increase in oxidation number, so we can say that zinc was oxidized. If we look at copper, we can see that it goes from +2 to 0, which shows that its oxidation state became more negative, so we can say that it was reduced. Okay, so now some practice determining what is oxidized and what is reduced. Okay, so before we do this, we have to determine what the oxidation state of each atom is. Since we learned this in the earlier part of the discussion, I'm just going to bring up the numbers. Boom. Okay, so first thing, what was oxidized? Well, we see oxygen goes from -1 to 0. That's an increase in oxidation number, so we can say that oxygen was the atom that was oxidized. We see manganese goes from +7 to +2. That's a reduction in oxidation numbers. We can say that manganese is reduced. Now, the reducing agent is the species that contains the atom that was oxidized. And the oxidizing agent is the species that contains the atom that was reduced. So our reducing agent will be H2O2 because it contains the oxygen that was oxidized, and the oxidizing agent will be the permanganate ion. All right, so let's look at the next example. There are oxidation numbers. We see chlorine goes from 0 to +1, which shows that it was oxidized. Chlorine also goes from 0 to -1 though in the chloride ion, so chlorine was also reduced. And this is entirely possible. One atom or compound can be both oxidized and reduced in a reaction, and that makes the oxidizing and reducing agent chlorine. Alright, the final example, there are oxidation numbers. We see that copper goes from 0 to +2, so we can say that copper was the atom that was oxidized. Gold goes from +3 to 0, so we can say that gold was reduced. Now our reducing agent will be the species that contains copper, and it's just copper, so the reducing agent is copper. And the oxidizing agent will be that which was, or that contains that which was reduced, so our oxidizing agent will be AuCl4-. Was reduced. Alright, so I want you to take a moment just to find the elements that were oxidized and reduced in each of these examples. So pause the video and go ahead and do that. Okay, in the first example, we see that chlorine goes from 0 to -1, which is a reduction in oxidation state, so chlorine was reduced. And we see that the bromide ion goes from -1 to 0, so potassium bromide was oxidized. Alright, in the next example, we see copper goes from 0 to +2, so copper was oxidized. And we see that nitrogen goes from +5 to +4, so it was reduced. And then finally, on the next example, we see iodine going from 0 to +5, so iodine was oxidized. And again, nitrogen goes from +5 to +4, so nitrogen, or nitric acid, was reduced. Okay, so balancing redox equations using the half reaction method. There's a series of steps that we have to follow. Now, sometimes you won't need to use each of these steps when balancing the equations, but sometimes you'll need to use them all. So it's good to go through in your mind the steps as you go so that you don't miss something. So step 1 says create two equations, one which shows the oxidation process and one which shows the reduction process. Second step is to balance all the atoms that are not oxygen and hydrogen. Step 3, we're going to balance oxygen by adding water to the other side of the equation, and then balance the hydrogens we added in water by adding hydrogen ions to the other side. Now we do that because we make the assumption that the reactions are taking place in acidic solution. If the reactions are not taking place in acidic solution, then essentially they're just ordinary reactions, and you don't need the half reaction method to balance them, or the ordinary redox reactions, I should say. Alright, so step 4, we're going to balance the charge by adding electrons to each side. Then it's important to note that electrons should be a product for oxidation and a reactant for reduction. And step 5, we're going to multiply one or both of the equations by a factor that will equalize the number of electrons lost and the number of electrons gained during the process. Finally, we'll add the reactions together, canceling out the species that appear on both sides. Usually it's just the electrons, but sometimes it's a little bit more. So let's look at some examples. Now, before I can pull the equations apart into their oxidation and reduction half reactions, I have to assign oxidation numbers. So zinc is 0, nitrogen will be +5, oxygen is -2, the zinc ion is +2, and nitrogen is 0. So I can see that in this process, zinc was oxidized. So we'll pull out the oxidation process for the oxidation half reaction, which just shows elemental zinc going into zinc ions. Now, we don't have to balance zinc here because it's already balanced. There isn't any oxygen or hydrogen, so we won't balance oxygen or hydrogen. Hold on. Sorry, I had a little error with my PowerPoint there. Okay, so we don't have to balance zinc, and we don't have to balance oxygen or hydrogen because neither of those things are in the equation. So all we have to do is balance the charge by adding electrons. Since the reactant side is neutral and the product side is a charge of +2, we'll add 2 electrons to the product side. Next, we'll find the species that was reduced. And we see that nitrogen goes from +5 to 0, so the reduction half reaction will show the nitrate ion going into diatomic nitrogen. Now, the first thing we're going to do is balance nitrogen, so we'll put a coefficient of 2 in front of the nitrate ion. Next, we have to balance oxygen, so we'll add 6 water molecules to the product side because we have 6 atoms of nitrogen on the reactant side. Now we have to balance the hydrogen we just added by adding 12 hydrogen ions to the reactant side, and then we're going to balance the charge. Well, the product side is neutral, and the reactant side has a net charge of +10 because we have 2 units of negative charge from the nitrate ion plus 12 units of positive charge from the hydrogen ions. So to equalize out that charge, we'll have to add 10 electrons. Now is where we're going to multiply one or both of the equations by a factor to equalize the number of electrons lost and gained. So we see that 10 electrons are gained in reduction, and we're showing 2 electrons being lost in oxidation. So we have to multiply the oxidation half reaction by a factor of 5. When we do that, we'll have 10 electrons on both sides of the equation, and so all the electrons will cancel out. Now we can add both reactions together to get the overall. Now it looks a little bit complicated, but it's always a good idea to check and see that your equation is balanced. So I see that we have 12 hydrogens on both sides. We have 2 nitrogens on both sides. We have 6 oxygens on both sides, 5 zincs on both sides. The total charge on the right side of the equation is +10 because we have 5 zinc ions. And the total charge on the reactant side is, man, I'm sorry, something is wrong with my PowerPoint. It's going automatically. It is also +10. So in the next example, we have elemental bromine, the bromate ion, and bromide ion. So we see that bromine is going to be both oxidized and reduced in this equation. For oxidation, we have bromine going to the bromate ion because bromine goes from 0 to +5. So we're going to first balance bromine by adding a coefficient of 2. We'll then add 6 water molecules to the reactant side to balance oxygen, and 12 hydrogen ions to the product side to balance hydrogen. Now we have to add 10 electrons to the product side because we have 12 units of positive charge from hydrogen and 2 units of negative charge from bromate. All right, so for reduction, we're going to show bromine going into bromide. Here we're going to have to balance bromine, and we'll have to add 2 electrons to the reactant side to balance the charge. Now, since we're balancing the charge by adding electron, we can only make a side of an equation more negative. So the charge doesn't necessarily have to be neutral, they just have to be equal on both sides. So now we're going to multiply the second equation by 5 to equalize the number of electrons, which will cancel out the electrons. When we add the equations together, we'll get 12 hydrogen ions plus 2 nitrate ions plus 5 zinc going to, oh my goodness, this slide was really hard to animate if you couldn't tell, so hold on one second. Okay, sorry about that. I tried doing this video about 100 times on my new smartboard and was having technical difficulties, so instead of starting over, I'm just going to fix that problem. All right, so when we add the reactions together, we get 6 waters plus 6 bromines, and notice we have 5 from the reduction reaction and 1 from the oxidation reaction that will add together to produce 10 bromide ions, 2 bromate ions, and 12 hydrogen ions. And if you check, this is fully balanced. All right, so take a moment and do these 2 examples all on your own. All right, so first thing we're going to do is assign our oxidation numbers. You should have gotten these. We see that iodide is oxidized into iodine, so we will balance iodine, and then we'll add electrons to balance the charge. We see that for reduction, we have the dichromate ion going over to chromium, or chromium 3, excuse me. So we'll first balance chromium, then we'll balance oxygen, then we'll balance hydrogen, and then we'll balance charge. Now I'm adding 6 electrons because the product side has a net charge of plus 6, so we need a net charge of plus 6 on the reduction side. And since we have 14 minus 2, that gives us a net of plus 12, so we have to add 6 electrons to make it plus 6. So we're going to have to multiply the oxidation half equation by 3 in order to equalize the electrons, and when we do that, we get this for our overall reaction. All right, so the next example, please mind the hydrogen peroxide, so, like I did not. So in this case, oxygen will have a charge of -1. All right, so these are all the oxidation states you should get. And we see that for oxidation, we have the oxygen in hydrogen peroxide going from -1 to 0. So all we have to do here is balance hydrogen and balance the charge by adding electrons. And for the reduction half reaction, we have chlorine dioxide going into the chlorite ion, excuse me. So chlorine is already balanced, oxygen is already balanced, so all we have to do is balance the charge. Now we will double the reduction half reaction in order to equalize the number of electrons. When we do that, the electrons will cancel, and the overall reaction becomes this. So if you didn't get this, go back to the beginning of the slide and try again. Okay, redox titrations. So in addition to acid and base reactions, we can also quantify the species involved in redox reactions. Now the formula to do a redox titration is very similar to the acid-base titration, only in this example we multiply each factor by the inverse of the stoichiometric coefficient for the species involved in that factor. So nu1 and nu2 are the stoichiometric coefficients of reactants 1 and 2. V1 and V2 are the volume of reactants 1 and 2 in liters. M1 and M2 are the concentrations of A and B, or reactants 1 and 2, excuse me, in moles per liter. So here's an example. Consider the following balanced redox equation. It says in a titration to determine the concentration of potassium permanganate solution, 28 cubic centimeters of the potassium permanganate solution reacted completely with 25 cubic centimeters of a 0.0100 molar solution of iron 2 sulfate. Determine the concentration of the potassium permanganate in solution in grams per liter. So this is just a standard plug and chug problem. So the first thing we'll do is list our variables. The problem tells me that the volume of permanganate is 28 cubic centimeters, which is 0.0280 cubic decimeters. It asks us to solve for the concentration of permanganate, so we'll call that X. Now N, or the number of moles of potassium permanganate in the equation, is 1. So N of potassium permanganate, will be 1. The volume of iron 2 ions is 25 milliliters, or 0.0250 liters. The concentration of iron 2 is 0.0100, and the number of moles of iron, according to the equation, the stoichiometric coefficient of iron 2 is 5. So our equation then becomes this. When we plug in all the values, we should get 1 times 0.0280 times unknown concentration is equal to 1 over 5, or 0.2 times 0.025 times 0.0100. When you plug in the numbers, you get the concentration of the permanganate ion is 0.00179 moles per cubic decimeter. But the problem asks us to give the answer in grams per cubic decimeter. Since our volume is already in cubic decimeters, we just have to convert moles to grams. We'll do that by multiplying by the molar mass of permanganate, which gives us 2.13 times 10 to the negative first grams per liter. Now these problems might look difficult, but literally it is just plugging and chugging. You're given all the factors except for one. One thing you must be aware of, this equation is not in the data booklet, so it's something you must know how to do. Alright, so biological oxygen demand and the Winkler method. So the Winkler method just uses redox titrations to determine the amount of dissolved oxygen in a sample of water. And this is important because the amount of oxygen required to organic matter is referred to as the biological oxygen demand. And if biological oxygen demand is greater than the amount of dissolved oxygen, then aerobic aquatic life cannot survive. Alright, so basically what that's saying, biological oxygen demand is the amount of oxygen that life needs to exist in water. And different samples of water will have different biological oxygen demands. We see some in the table below. Pure water has a BOD of 1. Untreated sewage, yummy, has a BOD of 350. Brewery wastewater has a BOD of 500. And slaughterhouse wastewater has a BOD of 3,000. So what those numbers are saying is that slaughterhouse wastewater would need to have a lot more oxygen dissolved in it to support aquatic life than pure water. Alright, so since biological oxygen demand is in parts per million, it's important that you know how to calculate parts per million. To do this, we just have to take the mass of the solute divided by the mass of the solution and multiply it by 10 to the 6th. So parts per million can be expressed as the mass of solute in milligrams divided by the volume of solution in liters. So this is an example of converting molarity into parts per million. Wants to know what the concentration of a sodium ion solution is if the concentration of that solution is 1.02 times 10 to the negative 4th moles per liter. Alright, so we know that the concentration of sodium is 1.02 times 10 to the negative 4th moles per liter. To get parts per million, we want milligrams of solute over liters of solution. Since the volume is already in liters, all we have to do is convert moles into milligrams. So the first thing I'll do is convert moles into grams by multiplying by the molar mass, and then convert grams into milligrams by multiplying by 1,000, and I get 2.34 parts per million. Finally, they may or may not ask you problems, either giving you the BOD and having you calculate the amount of dissolved oxygen, or having you calculate the BOD and comparing it to the amount of dissolved oxygen. So if you're given one of these problems, the first thing you're going to do is use that redox titration formula to find the BOD or the amount of oxygen dissolved. Next, you'll convert it to parts per million and compare to the values given to determine whether or not the water quality is acceptable. All right? So for the water quality to be acceptable, the BOD has to be less than the amount of oxygen in the water. Okay, and that is discussion 9-1. Sorry about the shakiness, but it is what it is. All right, bring any questions you have to class, and thanks for watching.